Welcome to the introductory module of large sample inference. Actually, in statistics, we have done small sample inference, we have done some small sample comparison of estimators, some performance comparison of tests in terms of power, but there are often we encounter some type of statistics whose sampling distribution is not easy to obtain. So, if we get some statistical procedure using such a statistic, the quality of inference cannot be judged. So, that is why we need the large sample theory. Large sample theory enables us at least to compare the performance or to evaluate the quality of inference for large N. However, the problem is how large is large. So, there is no clear cut mentioning of what is meant by large sample, but still we often observe that whenever we get sample observations exceeding 30, the large sample approximations hold good. So, in this module we shall discuss some applications and some scope of applications of large sample theory. So, the objective of this course or this module is to learn why large sample methods are necessary, and we shall illustrate the necessity by means of some real life examples. The role of asymptotic procedures in statistics is actually twofold. Number one, it enables us to find approximate tests and confidence regions in situations where the exact distribution of the statistic is not analytically tractable. And secondly, it can be used theoretically to study the quality of statistical procedures. So, now we shall give an overview of large sample methods in statistics. So, large sample methods in statistics is a general methodology for analyzing data sets involving a large number of observations. Drawing statistical conclusions from a given data set need a suitable probability model so that the behavior of the observations can be explained conveniently. With respect to the assumed probability model, the behavior of the relevant test or statistic is studied carefully so that precise conclusions can be drawn. For small data sets with well specified probability models, the behavior of test and or statistic can be evaluated exactly. Now, if the underlying distribution is not simple as binomial, Poisson, exponential or normal, the exact sampling distribution of the concerned statistic may be mathematically intractable, even for small number of observations. Quite naturally, the degree of complexity increases as the number of observations in the sample becomes large. But it is interesting to note that for large data set, the requirement of an appropriate probability law assumption is not as crucial as in small samples. For large data set, we only need to assume that the underlying distribution is a member of a broad class of distributions. Thus more robustness is expected with respect to the underlying distribution assumption when the number of observations is quite large. So, now we shall discuss some requirements in large sample methods. There are some natural requirements for a statistical method to qualify as a valid large sample method. If the underlying problem is an estimation problem, it is natural to expect that the estimator should be closer to the parameter with the increase in sample size. This is the well known property of consistency of estimators. Again, if the underlying problem is a hypothesis testing problem, it is natural to expect that the test should be able to detect a little deviation from the null hypothesis with more and more confidence. In statistical terms, this means we should be able to detect a little deviation from the null hypothesis with higher power. Of course, when the sample size becomes large. This property is related to the so-called consistency of statistical tests. Thus, the primitive requirement is to study conditions under which such convergence properties hold. The next requirement for a large sample procedure is to ensure that the approximated sampling distribution is convenient enough for application. If the approximate sampling distribution is a simpler one like normal, chi-square or exponential, easy applications are facilitated. In probability literature, this amounts to investigate the convergence in distribution or central limit theory. However, for a given setup, there are usually a number of procedures qualifying the requirements of consistency and convergence in distribution. Thus, the next and most important requirement is to select an appropriate procedure from the class of such procedures through some well-defined optimality criteria. For example, in the estimation problem, the optimality criterion might relate to variance minimization in some sense. Thus, we need to use an asymptotically optimal procedure to judge the quality of resulting inference. So, first we shall discuss different types of data in statistics. In a data set, observations are the measures of some quantity of interest. Depending on the quantity of interest, the observations are measured either in a continuous or categorical scale. The categories may be ordered or may not be ordered. Naturally, an appropriate statistical analysis must depend on the nature of observations. Thus, we shall consider both categorical and continuous data for development. Now, we shall give an overview of applications or say a broad scope for the application of large sample methods. The objective of statistical inference is to draw conclusions about unknown characteristics of population from the information contained in a representative sample. The most important is to select an appropriate probability distribution. Next, the compatibility of the assumed model with the characteristics of the available data is investigated. Then, appropriate parameter estimation or hypothesis testing is performed to know the unknown features of the assumed probability distribution. Naturally, a complexity is associated with the assumed model and it makes exact inference almost impossible. So, let us consider our first example. Consider the average marks in an examination for a group of n students. Suppose the objective is to extract some idea about the marks obtained by the students. The marks of the ith student is indicated by xi with f as the underlying distribution. Suppose there is sufficient evidence to assume that the underlying distribution is normal with unknown mean mu and unknown variance sigma square. That is, it is reasonable to assume that f is nothing but the family of normal distributions with mean mu and variance sigma square. With the specification of the underlying distribution as normal, we at once get the statistical properties. For example, if the problem is to estimate unknown parameters, then the maximum likelihood method or the method of moments can be adopted. With the specification of normal model, one can even go for finding MVUE, that is the minimum variance unbiased estimator of the parameters. In addition, if the objective is to test the null hypothesis mu equal to mu naught against mu greater than mu naught or some variation of these for known value of mu naught, optimum tests, that is uniformly most powerful and uniformly most powerful unbiased tests are also available. So, next we come to our second example. Suppose for a data set, the underlying distribution is justified as Cauchy with unknown location parameter mu and scale parameter unity. But with such a specification, the related inference is often complicated. For example, if the problem is to estimate unknown parameter mu, then the maximum likelihood method can be adopted. But no closed form expression for the estimate is available and numerical methods are the only option to solve the likelihood equation. Thus, it is almost impossible to investigate whether such an estimator is a minimum variance unbiased estimator or not. On the other hand, if the objective is to test the null hypothesis mu equal to mu naught against the alternative mu greater than mu naught for some known quantity mu naught, numerical methods are the only option, and hence optimality of such a test is not verifiable through any exact procedure. Now we pass on to our next example, that is example 3. This example is related to the famous Hardy-Weinberg equilibrium. Suppose the genotypes of a certain gene with two alleles A small a and capital A are labeled capital AA, capital A small a and small a small a. A random sample of small n individuals gives n AA individuals with genotype double capital A, n capital A small a individuals with genotype AA, and n AA with genotypes double small a. Naturally, the distribution of the vector n AA in or say the number of different types of individuals having different genotypes is multinomial with parameters n and success probabilities PAA, PA small a and P double small a. Suppose R and P are the allele frequencies with R plus P equal to 1, and equilibrium refers to the following expression for the success probabilities PAA equal to P square, P capital A small a equal to twice PR, and P small aa as R square. Naturally, likelihood methods can be adopted to find the parameter estimates. Even if we obtain a simple expression for the parameter estimate, the exact distribution is far from a tractable one. Thus, the investigation of the optimum properties of such estimators is not feasible. Consequently, an appropriate test in this context depends on finding the exact distribution. The degree of complexity increases with the number of categories and the number of unknown parameters. Let us consider our next example, which is on linear regression model. Suppose yi are independent observations and the yi has distribution fi, where fi are distributions but are not known. Suppose fi is normal with mean alpha plus beta xi and variance sigma square I. If sigma I are either known or at least equal, we get the classical homoscedastic regression setup. Inferences can be drawn until the above assumptions hold true. If the distribution is not normal or sigma I square are unequal, the inference becomes complicated. So, no exact properties can be studied with these assumptions. Suppose a population is divided according to a character A with k classes and also according to a character B with S classes. The objective is to judge whether the two characters are independent. Naturally, Pearson divergence measure is a relevant statistic, but small sample distribution evaluation of such a statistic is quite complicated. Large sample methods provide a way to carry out a test using such a statistic. The same is observed for a test of homogeneity. Next, consider example 6. Suppose the weight of each child, say y, is observed for p fixed randomly assigned diets, and the diets are indicated by x. If yij is the weight of the ith child given the jth diet and xij indicates the corresponding measurement of diet, we have a repeated measures model. One can use a random effects model with normal but correlated errors. However, if we deviate from normality, say some other member of the exponential family, or even consider a complex correlation structure, investigation of the exact properties become far from feasible. Now we shall discuss quality of inference, or how to judge the quality of inference in large sample. We start with some examples. Suppose we have a sample from normal mu sigma square population, where mu and sigma square are both unknown. The objective is to estimate mu square. Now consider the following estimate. T1n, which is nothing but mean square, that is x bar square, and T2n is nothing but x bar square minus s square by n. it is well known that T1n is the ML estimator and T2n is the minimum variance unbiased estimator. Now, if we want to compare the performances, MSE computation is the only option. For normal parents, MSE comparison is straightforward, but if the distribution is unknown, the performance comparison is not an easy task. However, one can check consistency at a minimum and then the rate of convergence for a valid comparison. As another example, consider comparing the performance of sample mean and sample median for estimating a location parameter. Naturally, the estimator with the lowest MSE is better, but computation of MSE is not an easy task. However, large sample methods always provides a way to compare the performances. We can compare the performances using consistency and large sample efficiency. Next, consider our next example. Suppose we have samples from a distribution with mean mu, with median mu. We use sample median for estimating mu. The natural question is to know for which distribution sample median gives the most efficient result. In small sample, such a comparison involves quite cumbersome mathematics. However, if at a minimum consistency and asymptotic normality for the estimator is confirmed, one can compare the asymptotic variances to get the answer. Suppose we have samples from a standard bivariate normal distribution with correlation coefficient rho. Maximum likelihood estimation of rho involves solution of a third degree polynomial equation. Due to intractable nature, property investigation for such an estimator is not possible. The problem becomes even more complicated if few observations are missing. However, large sample methods are well applicable in this situation and is perhaps the only way to get some idea about the performance. We have already indicated that carrying out any statistical test requires the knowledge of the sampling distribution of the concerned test statistic, but such distributions are often analytically intractable and depends on the distributional assumption of the data. For example, consider testing the null hypothesis mu equal to 0 based on n IID observations x1 x2 xn from a normal distribution with mean mu. The natural procedure is t-test based on the statistic Tn, which is nothing but square root of n multiplied by x bar whole thing divided by the sample variance Sn, say sample SD Sn, which has a t distribution with n-1 degrees of freedom under the null hypothesis. But often the assumption of normality is doubtful. Suppose it is only known that the distribution is continuous. Naturally, sign test is then one of the options. Now it is natural to ask how much we lose if t-test was used. Thus, we need to compare the performance of two tests. In small samples, the comparison can be done in terms of power, but such a power depends on the underlying assumption and alternative. If n is not too small, we often use the null distribution of Tn. We often use that the null distribution of Tn approaches a standard normal distribution. Then an asymptotically level alpha test is to reject the null hypothesis if the observed value of the absolute value of Tn exceeds tau alpha by 2. However, in large samples, one can compare the quality of inference using the concept of asymptotic relative efficiency. It is well known that if the underlying distribution is normal, t-test is the most efficient, but there are distributions like double exponential for which sign test gives better results. Thus, large sample methods provide a template to compare the performance of different tests. So, we have seen the scope of application of large sample theory in statistics, but as is evident from the examples that large sample theory, probability theory and real analysis are good companions of each other. So, our next module will be on the mathematical preliminaries for a best overview of the large sample methods.